Oh, there we go. Come on, man.
Yes.
So they can hear me out there?
Turn up your volume.
Well, yeah.
So turn your volume down again. They can hear you.
Exactly what it's supposed to look like. Okay.
And you have a minute.
I have a minute. I got a minute and 8 seconds.
Okay. Well, this box says you got 2 minutes. When I get it at the right angle.
What? That might be a good idea. Not too bad for yourself. That's good. Haven't seen you in a while.
I know. How have you been?
I'm still talking about it. I have been less than 2 years. Yes, I'm sorry.
Good experience.
Yeah. One of your seats on prime. Let's go. That did, you know.
It was really fun. It was a lot of fun there.
Well, they said we're going to do a meeting. They have just 2 rows of chairs right here. Good chairs.
Just to see what happens.
Cool.
Wait for 1 or 2 minutes. First time the seminar series.
Yeah, it's fun. And I'll pretty much introduce myself too.
Morning, let's start. And so we are having we're starting the cybersecurity seminar series, and so we are with pleasure and honor to have Dr. Nick Multari from PNL and to give the first seminar. And Nick has been a longtime friend for Iowa State and also at the Resiliency Center. We've been working together for many years so far. So in the seminar series consists of talks from both internal and external. We're going to have people from outside like Nick, and also have faculty and the graduate students to talk about their research work that is being done at Iowa State. So Nick has been is the lead for the asymmetric resilience cyberspace at PNL and the initiative lead. And also before that, so has taken positions as 20 years computer scientist at the U.S. Air Force and retiring as a lieutenant colonel. After that, so he worked for Boeing as the manager for strategic cyber technology for Boeing R&D, and so managed a really large program at Boeing. And so we worked together since then. Without further ado, I'd like to ask Lee to start the talk.
All that proves is I'm old. All right, as Guan said, Dr. Guan said, my name is Nick Multari. I'm at the Pacific Northwest National Laboratory, and I am a principal program manager of cybersecurity research there. And what I'm going to talk about today, the title says validation of asymmetric cyber resilience, but it's kind of broader than that I'm going to talk about. I'm going to talk about first what the motivation is, why ADP and NL get involved, what we did in order to kick off the research that we spent the last 4 years, now into the 5th year on. From there, I'm going to talk about some terms. Why? Because when we talk about cyber resiliency, when we talk about asymmetry, really, in order to create a true framework, we have to define these terms formally, mathematically. And the problem is, it's really hard to do. Matter of fact, in some cases, we're still looking for some of these definitions in mathematical terms. Once I talk about that, I'm going to talk about some of the research that we actually performed at the lab, how we're going about validating that. So I'll talk about the testbed, the experimentation, and still some of the questions that we have left. Now, as far as the motivation, it's relatively simple. Where did we start? We started many, many, many years ago. What was cybersecurity? Well, it wasn't even called cybersecurity back then. It was called information sharing code. Before that was automated information security. Before that, who the heck knows? But it was all based upon physical security. I had some type of asset I was protecting. I made sure that nobody got close. And that was really easy to do because there's no connectivity. What happens? We started connecting things up. And then, come on. Oh, we send the person running. But then they get smart. They realize there's connectivity and they start remote attacks. Now my asset is in danger. So what's the defender do? The defender says, oh, okay, so they're attacking using this methodology. What do? I will prevent them from using that methodology. I build a tent. I protect myself from these air attacks. Does that solve the problem? Heck no. Why? Because the attacker doesn't necessarily need to come at me the way I expect. Matter of fact, they probably won't come at me the way I expect. So, and they usually come up with a really cheap solution while I have an expensive solution. And they just come at me in a different way. What? You have logged in from another device. Messenger is now inactive. I don't care. That's in this one, not mine. Okay. So I'm making assumptions about what the attacker is going to do, and unfortunately, those assumptions are usually incorrect. They're going to come at me and they're going to surprise me. The surprise may be a rational move on their part. It may not be a rational move on their part. And it's that irrationality, in a lot of respects, that scares the living heck out of me. So where do we end up? We end up with this whole concept of a fortress. We have this wonderful permanent defense. We have a whole bunch of firewalls. We have a whole bunch of IDSs, and other three-letter acronyms. We have internal defenses within my network. And guess what? It's still not effective. All you gotta do is talk to places like Home Depot, Target, and the Office of Personnel Management, and Anthem Healthcare, and the list goes on and on and on. DOE. You know, I was at DOE for 3-4 months as an employee of the lab. I get this nice little letter from the CIO of DOE that says, "Dear Nick, you've been selected. We don't know who selected you, but we know you're one of 104,000 records that just disappeared." Makes you feel really, really good. This doesn't work. And I don't think anybody would deny that. So, looking at this issue from the lab perspective, and realizing that the attacker's always going to figure out another methodology to come at me because there are so many unknown vulnerabilities out there. We decided that probably the best thing to do is not necessarily look at cybersecurity as much as cyber resilience. And what do I mean by that? I want to be able to ensure that all the critical functions continue to operate, even when I'm under a successful cyber attack. My business is there for a reason. It may be sales, it may be customer service, or whatever. I don't want a cyber attack to be able to disrupt that. I want to be able to perform that mission even in a degraded mode at all times. Why? Because if it does disrupt it, what does that do to my bottom line? It costs me money. It costs me customers. It costs me reputation. A whole bunch of different things. So, what we decided to do was to look at theory, processes, methodologies, and algorithms. One of the nice things about being at PNNL is we are sponsored by the Department of Energy Office of Science. Being sponsored by the Office of Science, that allows us to start looking at a lot of the theoretics that are behind some of the issues that we're facing. That's why the number one priority we had was to look at the theory behind cyber resilience, to be able to understand from a scientific point of view, from a mathematical point of view, what does it really mean to say that I am cyber resilient? So we spent some time doing that. And eventually what we came up with was defining cyber resilience as a multi-constrained optimization problem. Why? Well, when you think about it, it's pretty obvious. It's an optimization problem because, in essence, there are three possible states I could be in. Operational, degraded, or hosed, non-functional. And I'm always, as a defender, trying to move from those bad states to better states, eventually to the operational side. So I'm always trying to optimize the performance of my system. But there are tons of constraints on what I can do there. There's policy that I have to follow. There are regulations that I have to follow. There may be laws that I have to follow. What technology do I have installed? All of these are going to put constraints, and therefore, that's why it was a multi-constrained optimization problem. And I can define that as pretty much a state machine with transitions between the states. So I now have my mathematical basis for what I mean by cyber resilience. And I can start using that as a foundation for determining what type of technologies that I really need to install in order to be able to optimize my performance of my system. That's part of that definitional problem. The other problem is, what do we mean by asymmetry? I mean, it's right there in my title of the slide, right? Asymmetric cyber resilience. What do we mean by asymmetry? And then once I understand what I mean by asymmetry, how am I going to test everything? How am I going to take these technologies that either I develop or others develop and test them, evaluate them? Evaluate them in a scientific way. And I'll cover that in a little while. How do I perform the experiments? What do the experiments look like? How do I evaluate the results? Is this technology truly resilient? Or is it not resilient? Is it resilient only in certain cases? So I still had a lot of stuff now that I had a basic definition, a mathematical definition for cyber resilience of what I still needed to do. So let's look at asymmetry. Asymmetry is interesting because it's not a property. In and of itself, for a single entity, it is meaningless. It has to be in relationship to something else. does something be symmetric with itself? Two arms, same length, they're symmetric. One arm longer than the other, there's an asymmetry between the lengths of the arms. Anything that you look at, when you're looking at that balance between two or more entities, they're either similar, symmetrical, or there are dissimilarities, which leads to an imbalance between the two. So that's how we're basically defining it. Disproportionate and exploitable. What do I mean? There are significant differences between the two entities, but there can be there could be these differences between the entities, but if the difference is not exploitable, it's meaningless. I can have a totally vulnerable server that an attacker has tons of tools to attack, right? That's disproportionate. But if it's not connected to anything, it's not exploitable. So that's why we say it has to be both, disproportionate and exploitable between two competing entities. And now when we typically think of this difference, we're thinking of it in terms of the attacker has all kinds of advantages over the defender. That's typically true. So we look at it in terms of threat. It could be a small entity going against a larger entity, but there's an imbalance in how much each is expending. The defenders may be spending a ton of money. The small entity may be spending a little money. And so there is this imbalance between the two. But guess what? It only takes one vulnerability for that little bit of money to be successful. A number of the attacks that I mentioned were related to that. And then you got the other case. You got an entity that's attacking that has all kinds of resources. Recent example of that is, according to news reports, Russia's been attacking the DNC. Well, you have a country with tons of resources that can bring any type of resources they want to bear on the problem against a private organization. Again, there's an imbalance here. There's an imbalance in resources, probably money, and a whole bunch of other things. So we typically think of it in terms of threat. But we can also look at it in terms of defense. If I can reduce my cost, for example, in defending my system, I just started improving my posture when it comes to asymmetry. How can I do that? Well, I mean, there are ways. Encryption. I can totally encrypt all my data so that even if it gets broken into, it's meaningless to the attacker. Well, encryption costs money, yeah, but it's probably not as expensive as a lot of other technologies I could bring to bear. So I basically is protecting my data at a lower cost. So this works in both favors. It works in the favor of the attacker, it works in the favor of the defender. And so, and as I said, that imbalance could be, of course, a wide range of attributes. Is this good enough, this definition? It is to a degree. The problem that I have with it's informal. It's qualitative, not quantitative. If it's not quantitative, I can't really measure it. It becomes very hard to measure. I got other terms in there, disproportionate. Really need to be able to define that, again, ideally in mathematical terms. A whole bunch of other concepts involved. How do I define all these terms? So there's still this problem of informality of the definition versus where I really want to be. Because the more formal I can get in my definitions, the better my framework in developing the technologies. So we started looking at this. And we said, okay, how can we make this mathematical? Well, I can define it as a scale, simple number. And I can compare the cost of the attacker against the cost of the defender, right? Asymmetry equals how much is the attacker spending versus how am I as the defender spending. And what that does is it plots it on a linear line. If we're both spending the same amount, I'm basically symmetrical. I'm in the middle. If the attacker is spending a hell of a lot more money than me, I am moving toward infinity. And I really, really, really want to be there. Where are we? In reality, I think we're in the other direction. We're spending a lot. They're not spending a lot. We're getting closer and closer to a zero value, which basically says I'm getting closer and closer to getting hosed again. Does this work? The problem is that it's a single dimensional measurement. It is a measurement, but there's a lot of other stuff involved. For example, how much do I value what I am protecting? How much does the attacker value the target? So there's at least one more term in here that we need to bring into play. So let's bring it into play. And now I have a vector, a little more complex. So I have now two terms. I have the value of what I'm trying, the value to me, the defender, that I'm trying to protect against how much money I'm putting against that. Versus what's that target value to the attacker versus how much are they expending to try to exploit that, to steal it, to disrupt it, to do whatever the heck they want. And I have the line of symmetry, but again, they're equal. The attacker is trying to increase in this half of the graph. Defender trying to go to that half of the graph. And that's the problem. This is where we are. We're spending a lot of money typically protecting valuable information. Matter of fact, sometimes we're spending a lot of money protecting crap. Data that I really, if it disappears, is no big deal. If I don't have access to it immediately, it's probably no big deal. On the other hand, the attackers pretty much know what they're trying to go against, and they're spending the minimum amount of money that they need to spend in order to get there. We really want to try to move down here. Again, where I'm not spending a lot of money. The neat part about this is this right here. It gives me another term in order to try to affect asymmetry between me and the attacker. Before it was strictly cost. I tried to increase their cost, I tried to reduce my costs. That kind of moved me one way or the other on that line. Now what I'm trying to do is I can also try to affect the value. A value to me, the value to the attacker. It's easier to probably affect the value of the data to the attacker. Again, I go back to that encryption example. I encrypt all the data. They're after the data. It's probably less valuable to them. Why? Because I am going to significantly increase that term for them. They have to break my encryption scheme. That's not, depending upon what encryption scheme I'm using, that's not necessarily cheap. So you look at this. You say, yeah, okay, now I'm dealing with value and I'm dealing with cost. The problem is, I still don't know whether or not this is complete. Does cyber resiliency itself play into this? Should that somewhere be a term involved in this? If I'm cyber resilient, I can continue operating my critical functions. Does that play and help move that asymmetric difference between me and the attacker? Does it move it more in my favor? I don't have an answer to that yet. Are there any other terms that are applicable that we haven't even thought of yet? And that's why I feel really, really uncomfortable with this mathematical formulation for asymmetry at this point in time. I don't feel it's complete. And if it's not complete, I don't have a really complete framework that I can use in developing my technologies. I mean, it helps. It gives me at least some things to focus on. But I think there's more to be done. And that's why I said, you know, in some cases, defining these terms is not necessarily easy. So how did we go about selecting what technologies we were going to work out in the lab, especially considering that we had a limited amount of funds and really a limited amount of time? The program is a 5-year program. Well, we're just beginning our 5th year. So what I really, really wanted to do was I wanted to understand what the landscape was like, who was working on what, who was doing what technologies, and then kind of focus in on what we saw as the gap areas. So for example, passive asset dependency discovery. I really can't do much of anything in protecting my system, either from a cybersecurity point of view or a cyber resiliency point of view, if I don't understand, number one, my mission, my critical functions, and what those critical functions depend upon, data-wise, hardware-wise, application-wise, etc. If something happens downstream, I need to understand whether or not that issue affects my ability to perform those critical functions. That was originally done manually, believe it or not. People would go in, they would talk to the SMEs, they would talk to the operators, etc., wherever they were involved in. And they try to find out, the application developers would try to find out what all of these dependencies were. And they put them down on paper. And guess what happens when you put something down on paper? About 5 minutes later, it becomes overcome by events, OBE. Why? Because something's changed. No environment stays static. So they started coming out with technologies that would start looking for these dependencies in an automated fashion. The trouble is, I needed to be able to track things as they went through my network. So what do? I either modify the packets, something in the header to be able to track sessions, or I put an agent on every system. In either case, I'm making a modification to my system. That makes people really, really nervous, especially if it's a really critical system. So what we decided to do was, the automated mapping was really important, but there was a lot of hesitancy because of the required changes. What if we did it 100% passively? We didn't require any modifications to packets. We didn't require any type of agents on any of the systems. And by just watching the traffic and monitoring the traffic in the form of net flow, et cetera, to be able to just pick logs that are being kept as is. We just use a number of different techniques, machine learning techniques, in order to start stitching together these paths. Why? Because all of these dependencies display some type of temporal properties. Something happens, followed within some time frame by something else happening. So for example, I make a web query. It goes from my client, probably to DNS, in order to find out the address of this server. to the server. The server then makes a back-end request to a database to get the data, and then comes back to me. Well, that temporal sequence will probably always occur with an exception, caching. So now you start having to take into account that there may be one or two things missing in these temporal sequences because of caching. But in general, I can look at these sequences and then be able to start picking out where the dependencies are, what the dependency structures are. And then I can take these dependency structures and actually map them to critical functions. So what this allows me to do then is to understand where all the critical elements are within my environment and do it without having to require any changes being made to the environment itself. Decision support. Every cybersecurity and cyber resiliency dependent system has technologies that are going to do something. They're going to do something based upon something that's occurring, whether it be an apparent attack, it be a system failing, or whatever. So I need to be able to decide what to do based upon what I'm seeing. The problem is, I don't always know all of the events, all of the information affecting what I'm doing or what I'm seeing. And I have to take that into account. So in other words, I need to quantify the uncertainty that's involved. So for example, game theory. Game theory is a really neat concept that I can run a game between two entities and then decide what my best move is based upon their last move. But there's some issues dealing with game theory when it comes to cybersecurity. Number one is, in game theory, I need to know what all the objectives are, what the objective of each team is. In reality, do I necessarily know what the objectives of the attacker are? No. Second thing, I need to know what all the moves are, so I can evaluate all the moves. In reality, do I know all of the moves that the attacker has? No. I need to know the cost of the moves. Do I know what all the moves that the cost of all the moves of the attacker? No. So there's a lot of uncertainty, and the reason that game theory pretty much hasn't been used in cybersecurity all that much. But what if I can incorporate the whole mathematical science of uncertainty quantification into a game? And now, yeah, I'm not getting the equilibrium that I would in a normal game. I'm not even getting the certainty of the move that I'm making. But I have a number of moves that now can be selected based upon probabilities. The probability of what is occurring. And eventually, may get to the point that the probability of what's occurring may be so low that I'm not willing to make any move. But somewhere along the line, we've got to take that uncertainty, we've got to incorporate it into our decision-making processes and come up with an uncertainty-tolerated decision support system. Homomorphic encryption. I love homomorphic encryption. I don't understand anything, but I love the concept. Homomorphic encryption is great. Why? Because when you think of encryption and data that's encrypted, when I'm going to actually operate on that encryption, what happens? I have to take the data, I have to decrypt it, and then I send it to the CPU. The minute it's decrypted, it's vulnerable. Homomorphic encryption gets around that. It allows the data to be operated upon while it's still encrypted. Neat stuff. There's a problem with it. And that is, it's only good for certain operations, predominantly mathematical operations. Addition, subtraction, multiplication, division. There's not a heck of a lot I can do in a real life environment with just addition, subtraction, multiplication, and division. what would be really, really helpful is a comparison operator. Be able to compare two entities, greater than, less than, equal to. There's a problem, though, incorporating a comparison operator. If all of that information and all those functions reside on the same system, don't ask me how, but I trust the mathematicians that we have at work that tell me this is true. If I have all that information, I can decrypt the data. If one machine can do the mathematical operations and the comparisons, I can decrypt the data. Doesn't help me. But there's a way around that. The way around that is I distribute the operations throughout my environment. And the more systems I distribute those operations to, the more secure my system becomes. It becomes harder and harder in order to be able to decrypt the data. Why? Because the attacker has to compromise all the systems involved in the computation in order to do so. But again, there's always this negative side. And that negative side is the more I distribute this, the greater the time it takes to complete an operation. To the point that right now it's infeasible to do this for real-time type systems. But the potential is there. We just need to figure out how to bring out that potential so that it can be used in most applications. So we've been working in that area. Model-driven situational awareness. Most situational awareness today is gotten by watching the system operate, being able to collect a whole bunch of parameters on what's occurring, logs, etc., looking at traffic, and deciding whether something is occurring or not. But we're wasting a lot of information, additional information that I have, that can also give me a lot more situational awareness about my environment. So for example, as I said up here, I found out what all my dependency structures are. Well, I can then graph those dependency structures, and now I have a graph of my system. But it's probably not complete, because if there are any systems out there that are not involved in critical functions, they're not included. But there's network mapping tools out there that will then provide that additional information. So in essence, I can get a detailed network map of my network with all of the critical dependencies highlighted. So how does that help me with situational awareness? I have a model of my environment. A model of the environment that, because it was done in an automated fashion, I could pretty much keep up to date, unlike the paper. Most engineering techniques use some type of model to determine the characteristics of an environment. Boeing uses it to create models of airplanes. There are models of cars, they put in wind tunnels, characteristics are determined, etc. Why can't we do something very similar to that in the cybersecurity world? Why can't we take the models that we have and start analyzing these models on a near real-time basis to get additional state information? So for example, why don't I take this model and look at the centrality of all nodes? What do I mean by centrality? Basically, how many in and out edges a node has. Basically tells me how connected a node is. And I rank order all of these nodes from the highest centrality to the lowest centrality. And I start removing them one at a time from the top. I see what my network does, how it responds, how it reconfigures itself. And the further down I get in that list, potentially the more robust, the more resilient that network is. If it breaks really quick, the partitions that maybe only removing 1 or 2 nodes is not too resilient. If I can get down, halfway down the list, for example, before the network partitions, it tells me something about the resilience of my network. So why can't I take these models and do a whole bunch of graph analytics on them? Spectral analysis, centrality, whatever else. And start getting more and more characteristics. So we've been spending a fair amount of time doing that. I'm going to talk about this in a few minutes. Tabletop, basically dealing with training. If we're going to build these technologies, we need to be able to verify them. We need to be able to test them. So we have to create a test bed. We wanted to make sure that the test bed was as realistic as possible. So we have a number of different traffic generation programs. One of them wired by MIT Lincoln Labs. And it really does generate traffic based upon you telling it what type of people, what applications they use, etc. The various technologies need to be able to go into this, whatever your configuration is, etc. You provide inputs. They may be legitimate. They may be illegitimate. And you see what happens. How does the system respond? What type of outputs do I get? Is the system still operational? Did it see the problem, adjust to the problem, and continue operating? And then when we started realizing what we're trying to do, we realized that we're really using an OODA loop, right? Orient, discovered on Cybersecurity. An OODA loop, though, looks to the outside. We want to look inside. We're looking at our own network. So we changed the name. I want to discover what's in my network and what's occurring in my network. I want to be able to take that information and reason about it to get situational awareness. I want to use that situational awareness to start making decisions on whether or not I need to do something. And if I need to do something, I need to act, need to execute. But guess what? The minute I execute, I change something. I need to discover what changed, and the cycle continues. We also needed to, because we're looking at critical functions, we need to build a company. A company that has missions, that has functions, sales mission, customer service mission, a development mission, whatever. Why? Because the attacker in cyber resilience is going to want to disrupt those missions. So on top of that test bed, we create this company. And this is an early version. We added cloud connectivity, for example. We added mobile capabilities to this. We actually bought a whole bunch of handsets and tablets and stuff to add to the test bed. But you know, it's built like a traditional company. You got your data center, you got your users, you got your connectivity. All of this is done predominantly through VMs. You know, when you do that though, and you're trying to get something to be as realistic as possible, you're throwing in artificialities in there, artifacts. And before you start running any type of experiments, you better understand what those artifacts are that you added in. Because those artifacts are going to have some effect on what you see. Give me an example. I said we're using MIT Lincoln Labs Lariat to generate the traffic, user traffic. That wasn't our first choice. Our first choice was an internally built user traffic generator. So we put it in there. And because some of the tools that we developed are looking very, very finely, for example, that asset dependency discovery, doing a lot of temporal analysis, we started noticing some anomalies like whole bunch of traffic be sent, no traffic sent, whole bunch of traffic sent, no traffic sent, whole bunch of traffic sent, no traffic sent. And trying to get that temporal analysis was getting near impossible. So we started looking, why is this occurring? And we found out that the user traffic generation tool was built that way. It does stuff, it sees what happens, it does stuff, it sees what happens. Well, guess what? That threw off all of our possible testing. And even though that gap was in the area of milliseconds, it didn't matter. It still was an artificiality that would have affected our experiments. So we got rid of that, and we went to Lincoln Labs and got their tool, which works better. So you had to be aware of what type of errors and what type of artificialities you're adding. All right, so now that we had this environment, we're ready to do our experimenting, our testing. And you would think that you would just test it like you would do some testing with cybersecurity. But then we started realizing, there are differences between cyber resilience and cybersecurity. So, for example, the objective the attacker in each case is different. Our assumptions are different. When I'm testing cybersecurity, I start the attacker from the outside of the network to say, get inside the network, get to this sensor directory or file, plant a flag there, poof, you do that, you won. Cyber resiliency, what's my main focus? My main focus is to continue operating those critical functions, even in the face of a successful attack. So I'll start the attacker already inside the network. They broke it in, that's a given. I'm not going to be able to stop them. So let's start them inside the network. The attacker's whole goal is to disrupt those critical functions. What defines success? In this case, the flag is planted. In this case, that's not. The attacker may be able to get to the critical directory, critical data, critical application, and do something to it. The question is can I respond to that action and get the system up and running again within a specific period of time? What defines that specific period of time really depends upon the function. In some cases, the function may be a real-time function, maybe monitoring SCADA system for electrical power, and an average that can be tolerated may be in the order of microseconds. So I have to be able to respond within that time frame. God bless you. In the case of our salary system, at the lab we get paid once a month. If the salary system goes down for 3 weeks, I don't care as long as it's up the last week of the month. So that time frame that you have to respond really depends upon the mission. And that's what we're doing here. We're saying that there are critical functions. Here are the time frames that the defender has to respond by. And if they don't, then the attacker wins. As long as the defender keeps responding within that time frame, they're winning. So there were differences between the red team for cybersecurity and cyber resilience. And we really wanted to bring this point home. So we didn't cheese the name. We're calling it an impediments team. Why? Because cybersecurity is strictly intentional attacks. When we're dealing with cyber resiliency, we got to deal with the intentional attacks, but guess what? I also need to deal with the fault tolerance issues. Just normal failures, because that can have just as much impact on my system and on my mission as an attack. So what we do is we allow the impediments team to do cybersecurity type of attacks, as well as potentially throw in a disaster here and there. How realistic is that? Well, just look at North Carolina right now. they're getting flooded. So it is. So it's predominantly intelligent attacks. We're going to run the experiment 3 times. The first time they have no information about the network. They have to find out everything by themselves, including what the critical functions are. The second case, we'll give them at least some configuration information. And in the third case, we will give them any information they want. And we'll see at what point do they become successful. Or ideally, hopefully, they'll never become successful. We are doing this using the technologies that are from the defender's point of view, the technologies that we developed, as well as external technologies. If anybody is interested in providing us a copy of what they developed and stuff, we'll throw it into the testbed. The other thing we want to do is to make sure that this whole testbed concept is run and follows the scientific methodology. What do I mean? I want to make sure that everything we do is repeatable, so it can be verified. I want to make sure that it's reproducible. So if somebody else wants to run the exact same experiment, they'll get the same results. I want to make sure it's portable. So what we're doing is we're taking that entire company, all the VMs and stuff, and we're bringing them here to Iowa State to be loaded on Doug Jacobson's Ice Age to see whether or not the system will run in that environment, or how much tweaking we need to do in order to make it run in that environment. So we have a lot of goals for this test bed. So that's basically where we are. The trouble is, where we are doesn't answer near all the questions. And we still have a ton of questions, especially dealing with this whole issue by asymmetry. Because I really believe that that's the key to cyber resilience. If I can start moving that needle so that I start eliminating that imbalance between the attacker and the defender, if I can create technologies, if I can create the theory that acts as the foundation for those technologies, that respond in a quick enough fashion that regardless of the attack that comes in, I can respond to it. And I can respond to it in a time frame that's required by my mission. And all that is really dealing with moving that asymmetric imbalance. Right now, as I said, we deal with defining it in terms of value and cost. I'm convinced there are other terms in there, just don't know what yet. But even in those terms, if I can reduce my cost or increase their cost, if I could reduce the value of their target against the attacker, I'm at least starting to move the needle. And that's what some of the technologies that we're dealing with are trying to do. The homomorphic encryption, for example. In other cases, they're there to try to make sure I respond within the time frame that I can. But the technologies I showed you complete, does it create a complete system? No, it doesn't. And that's why we're also dealing with external entities, bringing in some of their technologies. So that's where we are. These are some of the issues that we're still looking at. You got ideas? Email them to me. Because we really want to be able to do as much as we can before we're done. So that concludes my presentation. If there are any questions, I'm glad to try to answer. Yes.
And your definition of resilience, and I'm trying to think exactly how to phrase this, but it seems to me that in a lot of the situations that we've seen where an attacker goes in and gets data and then, is using that data for whatever reason, they're not taking down the network or they're not really degrading the performance of the organization. Sure. And so in your definition, that almost seems like, well, we're still successful. But I'm sure if you talk to the companies, the organizations who are breached, they would say, no, that's not a success.
Well, it depends upon how you define success from a corporate or government or whatever point of view. So, as you heard, my background is a lot of military there, 20 years in the Air Force. One of the critical data items that the Air Force has is air refueling schedules. And if somebody gets a hold of those air refueling schedules, they can send up fighters to knock out not only the fighter that's running out of gas, the bomber that's running out of gas, but the tanker too. So you really don't want the enemy to get that information and stuff. If they do get that information, that does impact their mission, and as such, does come into play. If losing that data doesn't really impact my bottom line, my mission, I don't care whether or not it disappears or not. So it really depends upon the organization that's looking at it, their perspective. From a purely definitional point of view, you're right. If the data gets leaked, it's not important to them, it doesn't affect their cyber resilience. If it is important to them and it does affect their ability to prosecute or to continue their game plan, if you will, then it does. And that's why we got things like the homomorphic encryption we're also looking at, because of that. But we did struggle with that first. Our first year, we asked ourselves the exact same question.
So you factor things like breach disclosure costs and the value of the asset? Is that how you're going to model?
Yes. Yeah. How much will the loss of that cost me? The value, reputation, it could be, and it doesn't have to be necessarily monetary. It could be reputation, for example.
Does your cost of event have to compete with cost to maintain that system? You're talking about the value is implicit. We have to have X, Y, and Z. So we're deciding how to defend it versus feature.
Up to this point, we have not included maintenance costs, mostly because it's something that has to be done regardless.
Well, maybe not maintenance, but feature improvements, feature enhancements that will continuing to increase the value of that system. It's a different point of view than perhaps some of
Yeah, I would say that whatever is of value to the using organization, that goes into the equation. Because again, value is not just, it'd be a range of different properties of it. So I know that's not a really good answer,
yes, more about
but it really depends upon the user organization. And that's one of the things about cyber resilience is that a lot of these things, especially that value term, really does rely upon the organization that is implementing this, as well as what's important to them. I'm just providing the tools and the foundation for it.
how do you overcome the temporal advantage that the attackers have? Your system has to be able to be defensible from the point it's conceived to the point you stop using it, and they just only have to spend more instead of attack.
Well, and that's the reason why we're looking at speeding up the decision-making process, for example, adding uncertainty, because if I'm trying to wait to get as much information as I can, it probably is too late. So that using models to get additional state information, so I have that in advance rather than just relying upon what I'm seeing occurring at that particular point in time. By using the models to properly determine where.
Response.
Right. So because I know where my dependency structures are, I know where to put my resources first. If I'm seeing an attack coming in, I can retrench and put my defenses around what's really critical and sacrifice potentially non-critical aspects. So there are things to help that can be done in order to help the resilience, not necessarily the security, because now they're inside the network and
prevention. It's about
right. Yes.
So you talk about security versus resiliency. There was that question. So there are two different dimensions. One has to do with observability, and confidentiality. And the other one is more about controllability. So in one case, the attacker is passively observing and getting access to confidential data and not affecting the system performance. The other one is tampering the data and affecting the system. Yeah. So those are two orthogonal directions, observability, and you could have asymmetry in both dimensions. So when you design a system, you would want the asymmetry to exist in both dimensions. For the user versus attacker.
Right. Yeah, I agree. The asymmetric issues they'll cover the security aspects, they'll cover the resiliency aspects. It's interesting when you look at confidentiality, integrity, availability, non-repudiation, and other aspects of cybersecurity, is that a lot of them do have to play into cyber resilience also.
Right.
Most people, when they think of cyber resiliency, automatically go to A, availability. But it's not necessarily the case. Integrity has a really, really large play because if I mess around with your data, I probably make you as inoperable as if I brought it down. Confidentiality when it comes to cyber resilience really does go into play and follows that first question. Because in some cases, confidentiality is important to the company and how they operate. In other cases, it's not. So the weakest link, I think, is the confidentiality link when it comes to cyber resilience. But integrity and availability are really great. Yeah.
So it seems the consensus is, the imbalance is really heavy in favor of the attacker. But have you been able to kind of use this model to say the cost of adding this new defensive measure is too high for us, or is it always kind of like, no, we need it anyway?
No, I mean, that's why we're trying to make sure that asymmetry is measurable, and that's why we're trying to come up with these different mathematical definitions, is to do exactly that. A good part of this has to do with risk and how much risk tolerance I have and stuff. That comes into play here. That's part of your cost. Yeah, I mean, that's our ultimate goal is to have these formulations actually being used in the risk analysis, et cetera, so they can make those type of determinations based upon the value, based upon the cost, based upon the attackers, the threat model, et cetera.
So following with that question, so have you done anything with the group in the fifth year, the beginning of the fifth year project? Have you done anything to quantitatively evaluate the asymmetry advantage?
From a technology point of view, our main focus this year is validation of what we have done. So using a testbed, porting the testbed, et cetera. We're still spending some time, but more or less looking at the formalities, the formal definition for asymmetry, seeing what we're missing. But as far as developing any type of technologies to try to move that needle, at this point, we're done. Yeah.
You talk about asymmetry in terms of the cost of the attacker and defender. So I was just thinking, is there any limited money we can spend as a defender on the industry side? Like, if I find out that this is a critical asset, how much money we are willing to spend on the industry side? So do we have any kind of real practical cases there?
Yeah, I mean that's going to depend upon each company, each industry member. Smaller companies are obviously going to be able to spend a lot less money doing the defense than a large company. So again, we're providing the analytical tools, but that's an issue that would have to be dealt with by the company itself, based upon its own circumstances.
And if this is not questions, okay. Let's thank us.
I like evangelists. That sounds good.
Next week at this time, we do another seminar that will be delivered by Professor Liu Gong, a new professor, and I was about this research. See you next
This is good. Cool. What area you use?
Yeah, I just see some charts here.
Yeah, that's great.
Hello,
My name is Dan.
My name's Cameron. Did I know, I don't think I heard about that. Yeah, I mean, a lot of people are in the market too, analysis, stuff like that. I never really got too much about cybersecurity, but